Okay, good day. This is Dual Enrollment Pre-Calculus. I am Mr. McCulley, and this is lesson number 29, the Law of Sines. Let's get to it. Today, we are going to use the Law of Sines to solve oblique triangles. We're going to find the areas of oblique triangles. We're going to use the Law of Sines to solve problems. Um, let's talk about what the Law of Sines does and what the Law of Sines doesn't. We've been talking about sine, cosine, and tangent quite a bit, usually in the context of right triangles. This is going to be to solve oblique triangles, so triangles that do not have right angles in them. And so what is the law of sines? The law of sines is set up as a proportion of three equivalent values. Now you will never use more than two at a time, but all of these ratios are equal according to the law of sines. Now, we can use this to solve for unknown pieces given that we know 3 of 4 given pieces. So just as a for instance, if I were to just, and we're just going to cross that out, if we were only going to talk about these two pieces of the extended ratio, excuse me, the extended proportion, if I knew what the angle A was, little a, and angle B was, I could solve for little b. So if I can know any 3 of those 4 parts, I can solve for the remainder. Now the law of sines works best when the known information is the form angle angle side or angle side angle. And I know that sounds like a geometry term for proving congruent congruent triangles, but when I say that the known information is that I know two angles and then the side that's not in between them, or I know two angles and the side that is in between those things. That means the law of, if you get that kind of information, the law of sines works very well. It's not quite as good for if you're given two sides and an angle. This is called the ambiguous case, and we're going to discuss that later. If you are given three sides, though, you cannot use the law of sines. You must use the law of cosines. Or if you're giving two sides with an included angle, you must also use the law of cosines. So let's do a quick example here. It says solve the oblique triangle, and so we're given three pieces of information. And if I were to label what the given information is, I have two angles with an included side. So this would be an angle side angle situation, and clearly from our given information, this is going to be a nice easy one to work with. We don't have to worry about an ambiguous case yet. And so basically what I'm going to do is I'm going to write down all of the parts. So angle A, angle B, angle C, little a, little b, and little c. And we're given angle A to be 32 degrees, and we're given little c to, or excuse me, angle C to be 46 degrees, and the side opposite angle B is going to be our little b, which they say is 10 meters. So if we're going to go through and we're going to solve all of this, we can use the law of sines. But we don't have to use the law of sines for everything because we are given two angles of a right triangle, or not a right triangle, two angles of a triangle, and we can use the Triangle Sum Theorem to say that since all triangles in a plane have 180 degrees as their angle sum, we can just subtract these two from 180 and get the correct value. So if I go 180 and I go subtract the 32 for angle A and the 46 for angle B, I will get 102 degrees, and that is the value for angle B, 102 degrees. 102 degrees. Now, because I've found that, I have a pair of parts, an angle and the side opposite that. So what I can do with that is I can use that to fill in one of these ratios in the extended proportion. So here's what I'm going to do. I'm going to solve for little a, and so I'm going to set up the given value. I know that the sine of 102, this angle right here, and it over its opposite side, 10, will be equal to, and again, we're trying to solve for a, the sine of big A, which is 32 degrees, over its opposite side, little a, which would be right here, and little c would be right there. So cross multiply and divide, and I'll get a equal to 10 sine 32 over the sine of 108. And all we have to do is plug that into a graphing calculator. So let's pull up the graphing calculator. We've been working in radians a lot, so we should check to make sure we are in degree mode. We are not, so we're going to bop down here and change this to degree mode. Hit quit, and then I'm just going to type the expression from the last page into the graphing calculator. And that is, so I need a fraction there, so I'm going to go alpha 1. I'm going to bring up my fraction bar, and we'll have, let's see here, it was 10 sine 32, and then we need that to be divided by, let's go down, make sure we're down, the sine of 108. Close that parenthesis, hit enter, and we get 5.572. So a little a, 5.572. All right, so to solve for little c, we're going to do essentially the same thing. Now, we've already used a derived answer, so I don't want to use this number here. So I'm going to set it up using the original ratio that I had from the first one, and I'm going to say that the sine of 102 degrees over 10, I know both of those parts, is equal to the sine of 46 over c, the angle and its opposite part. Now, I don't have to do a whole lot of work, the same thing. I'll get c equal to 10 sine 46 all over the sine of 102. Now this expression is almost exactly like the expression that we used before. We only have to change the sine of 32 to the sine of 46. So when I go to my graphing calculator, I'm just going to go second entry, bring up that expression again, and go up to the top and type in 46, and we'll type over the 32 from the last one. We're going to hit enter, and we get 564. So 7.564 equal to 7.564, 7.564, and that solves the oblique triangle. All right, let's get to the hard part. Side, the ambiguous case comes from the fact that the result of sine theta in the first and second quadrant have two equal solutions for each positive value. Now what I mean by that is, if we go back to our unit circle, if I say if I have 30 degrees, right, the sine of 30 we know to be equal to a half, but there is a second value, angle here, a second, we'll call this theta prime. There is a sine of theta prime that is also equal to a half, and we know that that theta prime is equal to 150 degrees. So there are two possible angles that have the same outcome. Now that doesn't mean that we're always going to have two possible solutions, but there are some instances in which there are. Now I think I have it all on here, but I'm going to bring it up first. There are actually 6 different instances, and I can't possibly do a better job than the textbook, so you're going to have to crack open your book and look at page 406 to see all of the possible cases. But the one that's going to cause us the most work is when we have a situation like this, where we have a side opposite a known angle that is between the height and the side adjacent to the known angle in total length. And what happens is, because of the fact that we could have two possible solutions, we could have an angle A, and I can only do this in an animation, but we could have an angle that doesn't change, a side B that doesn't change, a side A that doesn't change in length, and have two possible solutions. And then this third side here changes to two different values, and this third angle here and this angle there have two possible solutions. Now that's the only instance where those two values are going to be, or we're going to have two solutions. In the case that this angle A, or excuse me, this angle, this little side A is actually shorter than the height, then it never actually touches, so we have no solutions. If that little a is equal to the height, we'll actually have only one solution, because we'll have a right triangle there. If little a, I didn't write it here, if little a is actually longer than little b, we could only have one possible solution, even if a is both an obtuse and an acute angle. If it's actually longer than b, we could, let's say it's longer than b, we could only have one solution. We'd have to extend this angle out there, or that side out to there, to actually get that. So there's a bunch of different possibilities, and again, I suggest that you look at that page 404 to see them all. So just a real quick little process of how we're going to determine the ambiguous case. We're going to draw the diagram. We're going to find the length of h. We're going to compare a, b, and h, and decide which instance applies. And again, there are 6 instances on page 406. We're going to make a decision based on that number 4, and then we're going to solve. And so here in this next one, I have given you specifically a oblique triangle that has two solutions, and we're going to go through solving both solutions. But first, what we should do is we should go through that process to show, in fact, there are two solutions. All right, so I'm going to draw this triangle thusly. I'll draw it like this, and I'm going to label this little side A, and I'll label this side C and this one B, just because of the way that the values are given, so that I can type in all the stuff and set it up the same way each time. So I have a 10 there, I have a 9 there, and I have an angle 60 degrees right there. And so this side right here is going to be the height of that particular triangle. And so we want to figure out what that height is so we can do a comparison. And so we got to figure out what h is. Well, if this is a right triangle here, then the 10 is the hypotenuse of this right triangle. And so using just your standard trig functions, this side would be the opposite in this littler triangle. So I could say that the sine of 60 is equal to 10 over, oops, I did that wrong, because it would be opposite over hypotenuse. So it'll be h over 10. And so h equals 10 sine 60. Now we can do the exact value of 10 sine 60. The sine of 60 is square root of 3 over 2. But we want to do a comparison, so I'm going to put it in the calculator and go 10 sine 60 and get 8.660. And so clearly, the little a side, 8.660 is less than 9 is less than 10. So that's going to tell us that there are two cases, two solutions. All right, and that solution, the first solution is this triangle, and the second solution is that triangle. So B will be big here and very small there, and C will be acute here and obtuse there. So I'm going to write it this way. I'm going to go angle A, angle B, angle C, little a, little b, little c. And I'm going to go solution 1 and solution 2. Now, the values that are given don't change. So in solution 1, angle A is 60 degrees, and in solution 2, angle A is 60 degrees. Little a in solution 1 is 9, and in solution 2 it's also 9. Little c is 10 in solution 1, and it's also in solution 2. All right. So the first thing we're going to want to find is this angle right here, because it changes. And I need to do that because I have at least a piece of information that's given there. And I have, using law of sines, I have an opposite pairing. I have this 60 degrees and its opposite side. And so I can use the law of cosines to solve for the first angle of C. So I'm going to set that up like I did in the last problem. It'll be the sine of 60 over 9 is equal to the sine of C all over 10. And so we're solving for C, so cross multiply and divide and take the inverse sine of both sides. We'll get the measure of angle C is equal to the arcsine of 10 sine 60 all over 9. And so I go to put that in my calculator, second sine, and then we'll get a fraction bar in there. And what did I say it was? It was 10 sine 60 all over, go down, all over 9. Close that parenthesis there. Hit enter, and we get 74.207. So little c, 74.207, and around that, 207 degrees. All right, so this little c represents the obtuse angle, and what we have to find, leaving everything else the same, is what would that angle be? Well, it's actually fairly simple to do if we go back to this expression here. How do I figure out what that second possible angle is? Well, clearly this portion right here is 30 degrees. And so if I go all the way over, it's 180 degrees. If I subtract away the 30 degrees, I'll get the 150 that I had. So to find the second unknown value for this one, all I have to do, and I'm going to call it, just for the sake of argument, I'm going to say that this value here was 74.207. That's C. And so the second C, we'll call it C prime, is 180 degrees minus the original C. And so if I go back to my calculator and I go 180 minus second, oops, don't want to do that. Let's delete that. Second answer, I'll get 105.793. So 105.793. So 105.793. So that goes here, 105.793 degrees. And again, that gives me this particular angle C here, and clearly it looks like it's going to be an obtuse angle. And so I have that. Now to find B, B is going to be an acute angle there, but it's going to be a really small angle for that one. And I'm just going to use that Triangle Sum Theorem again. And so here's what I'm going to do. I'm going to go 180 minus the 60 that we were given minus the 74.207 that we got in that first one. I'm going to hit enter there, and I get 45.793. So that's my first B. 45.793. And to find this second B, I'm just going to do the same thing, except instead of the 74, I'm going to use the 107. And so 180 again, minus the 60 that was given, minus the 105.793 that we found for our second possible solution, 14.207. 7 degrees. All right, so all I have left is to find my b's. Well, I'm gonna, and just so I can keep everything, you might want to do it underneath. I'm going to erase right here. Again, I'm going to use the law of sines. Now, I'm going to have to use derived answers here. There's no choice. But certainly, I want to use as little as possible. So I'm going to set both of these up using some given information. And I'm going to say that the sine of 60 over 9 is going to equal to, and we're solving for little b, so I'm going to use the first solution there, the sine of 45.793 over little b. And cross multiply and divide, I get b equals 9 sine 45.793, this is not a very good 9, all over the sine of 60. Alright, so we go to our graphing calculator, we plug that in, and we get, let's see here, it'll be, let's make it a fraction. So alpha fraction, the sine, or excuse me, I need a 9 first. So 9 sine of 45.793, close the parenthesis, all over the sine of 60 gives me 7.449. Okay, so my B is 7.449 right there. And to do it again, you'll notice that if I set it up, it'll be sine of 60 over 9 equals the sine of 14.207 all over, we'll call it B prime, to have that second B. Well, it's going to end up being the same thing as the first one, except instead of 45.793, I have 14.207. So I'm just going to go back to here. I'm going to go second. I'm going to go entry and change this one. Oops, don't want that. Up, over, and hopefully it'll just let me type over. It'll be 14.207. Is that right? 14.207. Yeah, okay. And so I hit enter. I get the 2.551. And so B prime 2.551, 2.551, and that is my answer. Okay, last thing here, the area of an oblique triangle. We know that the area of any triangle is a half base height. So if this is my height and this here is my base, all right, let's say, as a for instance, I had this side, little a right there. And I wanted to figure out what the h is. So let's say I know what a is, and I have this b here. So if I know what a is, and I know what this theta is, right, I can say that the sine of theta is equal to the hypotenuse, or excuse me, this height, this opposite side over a, which would be the hypotenuse. And so I can solve for h, and I can say that, and I just get h by itself by multiplying both sides by a. A sine theta is equal to the h there. All right, so if I start with 1/2 bh, and I replace the h with this expression, a equal to 1/2 the base times the replaced h, a sine theta, and since it's all multiplication here, let's rewrite it and say it's 1/2 AB sine theta. So what this allows me to do is I don't always have to have an h. If I have two sides of a triangle, any triangle, with its included angle, I can find the area of that triangle by going 1/2 AB sine h. And so what does that mean? If I have a triangle, and I'll just draw that real quickly. Clearly the B is an obtuse angle. So I'm going to go B here, A here, C there. I'm going to go 130 degrees there. Little a is 92. Little c is 30. So I didn't really draw it to scale, but that's okay. So I have two sides with an included angle. If I go A equals a half AB sine theta, there's my theta, there's my two included sides. A equals 1/2 92 times 30 times the sine of 130 degrees, and we'll just go to the calculator. 0.5 times, what did I say? Sorry. 92 and 30. 92 times 30 times the sine of 130. Make sure I got that right. Yep. Close the parentheses, hit enter, and so that particular triangle has a area of 1057.141. So A equals 1057.141 units squared. That's all I got. So today, a lurid one. Ooh. Soap opera. In her 2016 memoir, Carrie Fisher revealed that during the filming of A New Hope back in 1974, she and Harrison Ford had an affair. At the time, she was only 19 years old, and he was 33, and he was married. Ooh. I'll see you in class, folks. Have a good day. Bye.